The solid state of matter is characterized by strong interparticle forces of attraction. As a result, most solids have definite shape and volume, which change only slightly with change in temperature and pressure. The smallest constituent particles of various solids are atoms, ions or molecules. All such smallest constituent particles of solids will be referred to as particles in this chapter. Types of solids. There are two types of solids, namely crystalline solids and amorphous solids. Crystalline solids. Study of many crystalline solids indicates that they possess the following characteristic properties. There is a regularity and periodicity in the arrangement of constituent particles in crystalline solids. The ordered arrangement of particles extends over a long range. 2. Crystalline solids have sharp melting points. That is, they melt at a definite temperature. 3. All crystalline substances except those having cubic structure are anisotropic. What is anisotropic? The ability of crystalline solid to change values of physical properties when measured in different direction.
Is the general representation of a crystalline solid. Using this general representation, let us draw two lines, one passing green, purple, other passing through purple. So from here I can say that in one direction the composition of the solid is green, purple, and in other case the composition is purple. In both direction, the composition of the particle is same or different? It is different. So since the composition of the solid changes with direction, we can say that the value of the physical property also changes, and that's the reason for anisotropy.
This is the crystalline structure of the solid. So when you measure from this direction, you can see the arrangement of the atom is different. Here the all purple color atoms are there, and it is very small size. And in other direction, if you see, it is very small size, big size, small size, big size. Here the atom arrangement is different. Since the atom arrangement is different, so the physical properties such as refractive index, thermal conductivity, electrical conductivity is different. When you measure from this direction, the electrical conductivity will be different, and when you measure from another direction, the electrical conductivity will be different. So when you measure any physical properties from different direction, the property will get differ, and this property is known as anisotropy.
What physical properties changes due to anisotropy? Refractive index, thermal, and electrical conductivity, etc., are different in different directions.
So here if I measure the refractive index from here, it will here it will bend in some angle, suppose 10 degree, but if I pass the light from here, it will bend at the 20 degree, more than 10 or less than 10, means it will be different. Means what, if you measure the refractive index from different direction, you will get a different value of refractive index if you measure from different direction. Same thing here, monoclinic. If you see here, if you are passing the heat from this direction, here the number of atoms is very less, so the heat will pass very fast. But if you see here the number of atoms is more, so here the heat will be pass very slowly. Okay, so thermal conductivity is changing, refractive index is changing. Here same thing here, current also. See here. Here the current is moving very fast because the less number of atoms are there, so less hurdles is there for the charge to move, therefore the faster will be the electric current here in this direction. But from here, if you see, the number of atoms is more, therefore the electric current will be less. So electrical conductivity is changing if you are measuring from different direction. So that's why they have mentioned that physical properties as a refractive index, thermal conductivity, electrical conductivity are different in different direction, and such property is known as what? Anisotropy.
Examples of crystalline solid: ice, salts such as NaCl, Metals such as sodium, gold, copper, and materials such as diamond, graphite, ceramics are examples of crystalline solids. Isomorphism. Two or more substances having the same crystal structure are said to be isomorphous. In these substances, the chemical composition has the same atomic ratio.
Or look at this isomorphous. Example, sodium fluoride, NaF and Mg. Both of them have something common, and that is the atomic ratio, which is 1:1. Sodium is 1, fluorine is 1, magnesium is 1, oxygen is 1. So the atomic ratio is 1:1. Similarly, if I take NaNO3 and CaCO3, the atomic ratio is 1:1:3. Isomorphous means two or more substances having same crystal structure, provided they have the same atomic ratio. If the atomic ratio of two examples are same, then they are called as isomorphous. They will always have same structure.
Polymorphism. A single substance that exists in two or more forms or crystalline structures is said to be polymorphous. Here sulfur exists in two-form rhombic sulfur and monoclinic sulfur. Polymorphs of a substance are formed under different conditions. Here rhombic sulfur is stable below 96 degree and monoclinic sulfur is stable above 96 degree. Polymorphism occurring in elements is called allotropy. For example, three polymorphic, allotropic, forms of carbon are diamond, graphite and fullerene. Other example of polymorphous: calcite and aragonite are two forms of calcium carbonate. Alpha quartz, beta quartz and cristobalite are three of the several forms of silica. Characteristics of amorphous solids. Random arrangement of particles. In amorphous solid, the constituent particles are randomly arranged. The particles do not have long-range ordered structure, but they do have a short-range order. Amorphous solids are isotropic. Their properties such as refractive index, conductivity, are all independent of direction of measurement. Since amorphous solids are randomly oriented, they exhibit the same property in every direction.
Point is about the examples, where the examples are tar, plastic, rubber, glass, lamp black, coke, charcoal, and etc.
Classification of crystalline solids. Crystalline solids are further classified into four categories: ionic solids, covalent network solids, molecular solids, and metallic solids. Classification of crystalline solids. Ionic crystals. Ionic crystals have the following characteristics. The constituent particles of ionic crystals are charged ions. The cations and anions may differ in size. The particles of ionic crystals are held by electrostatic force of attraction between oppositely charged ions. Ionic crystals are hard and brittle. They have high melting points. 4. Ionic solid are non-conductors of electricity in solid state. However, they are good conductors when melted. Ionic crystal when dissolved in water conduct electricity. Example of ionic crystals. Sodium chloride NaCl. Potassium sulfate K2SO4. Calcium fluoride CaF2. Potassium chloride KCl.
Covalent network crystals. Characteristics of covalent network crystals are as follows. 1. The constituent particles in covalent network solids are atoms. The atoms in these crystals are linked by a continuous system of covalent bonds. The result is a rigid three-dimensional network that forms a giant molecule. The entire crystal is a single molecule. As a result of rigid and strongly bonded structure, covalent network crystals are very hard. In fact, they are the hardest and most incompressible of all the materials. These crystals have high melting and boiling points. The electrons are localized in covalent bonds and hence are not mobile. As a result, covalent solids are poor conductors of heat and electricity.
Diamond. It is the most precious crystal used in jewelry, and it is an allotropic form of carbon. All carbon atoms in diamond are sp3 hybridized carbon atoms, and the bonding continues in all directions to form a big, giant network of covalent solids. The strong covalent bonds between sp3 hybridized carbon atoms make diamond a very strong and hard solid. It is in fact the hardest material with very high melting point of 3550 degrees Celsius. Graphite is another allotropic modification of carbon. All carbon atoms in graphite are sp2 hybridized. Know that the ground state electronic configuration of carbon is 1s2, 2s2, 2px1, 2py1, 2pz0. And hence, to stabilize the entire symmetry, we can say that an electron from 2s2 will jump into 2pz, which was 0. And once it jumps, this becomes an excited state electronic configuration having 1s2, 2s1, 2px1, 2py1, 2pz1. And this excited state electronic configuration will further jump into something called as hybridized state electronic configuration, where 2s1, 2px1, 2py1 will merge to give us a hybridized orbital, which is called as an sp2 hybridized orbital, leaving behind 2pz orbital, which is called as an unhybridized orbital. Each carbon atom is covalently bonded to 3 other sp2 hybridized carbon atoms and form interlinked 6-membered rings of carbon atoms. The remaining half-filled unhybridized 2pz orbital is used for pi bonding so that layers of carbon atoms, that is graphite.
Example of covalent network crystals. Diamond. Quartz, SiO2. Boron nitride. Carborundum. 3. Molecular solid. 3. Molecular crystals. Example of molecular crystals. Substances such as Cl2, CH4, H2, CO2, O2. On solidification give molecular crystals. 3. Molecular crystals explanation. The constituent particles of molecular solids are molecules. Consider molecular solid. Example: solid dry ice. Here solid dry ice is made of many constituent particle. And here all constituent particles are molecule, that is carbon dioxide molecule. Or in bonded single atoms of the same substance. 2. The bonds within the molecules are covalent. 3. Type of intermolecular force of attraction between molecules. 1. Polar molecular solid, weak dipole-dipole interaction. Weak dipole-dipole interaction. In polar molecules such as solid HCl, solid sulfur dioxide, benzoic acid, etc., which possess permanent dipole moment. Here the bond within the molecule are covalent. The molecules are held together by weak intermolecular force of attraction, e.g. HCl. Here HCl interact with other HCl molecule by weak intermolecular force of attraction. Due to weak intermolecular force of attraction between HCl. HCl is gas at room temperature. Below freezing point -114 degrees Celsius. HCl is solid at room temperature. The solid sulfur dioxide, SO2, obtained approximately at -72.7 degrees Celsius. Polar molecular solids are soft and have a low melting point. This is because of weak intermolecular attractive force. Here, HCl is attracted with another HCl molecule by a weak intermolecular force of attraction. This type of solid, that is polar molecular solid, are poor conductor of electricity and therefore it acts as a good insulator. Two. Non-polar molecular solid, weak dispersion or London force. In non-polar molecules such as solid CH4, H2. In monoatomic solids like argon, neon. These substances are usually gases at room temperature. Other example of non-polar molecular solid. Solid iodine. Here iodine is bonded with covalent bond. But iodine molecule interact with other iodine molecule by London dispersion force. This result in solid iodine. When solid iodine is heated, it get easily converted into iodine gas because of easily breaking of weak London dispersion force. In the video you can see solid iodine is converted into iodine gas. Three. Intermolecular hydrogen bonding. The electrostatic force of attraction between the positively polarized hydrogen atom of one molecule and a highly electronegative atom of other molecule is called hydrogen bonding. In ammonia molecule there is hydrogen bonding between nitrogen atom and hydrogen atom. Similarly hydrogen bonding in hydrogen fluoride between hydrogen atom and fluorine atom. Example of intermolecular hydrogen bonding. Solids such as ice H2O, ammonia NH3, hydrogen fluoride HF.
4. Metallic crystals. These are crystalline solids formed by atoms of the same metallic element, held together by a metallic bond. Metallic bond. In a solid metal, the valence electrons are delocalized over the entire crystal, leaving behind positively charged metal ions. Therefore, metallic crystals are often described as an array of positive ions immersed in a sea of mobile electrons. The attractive interactions between cations and mobile electrons constitute the metallic bonds. Metallic crystals have the following properties. Metals are malleable, that is, they can be hammered into thin sheets. Metals are ductile, that is, they can be drawn into thin wire. Metals are good thermal conductivity. Here, when metal is heated at one point, heat is transferred to other point. Metals are good conductor of electricity. Here, when metal rod is added to open circuit, bulb glow. It indicate that metal are good conductor of electricity. Examples of metallic solid. Metals such as sodium Na, potassium K, calcium Ca, lithium Li, iron Fe, gold Au, silver Ag, cobalt Co, etc.
Properties of 4 types of crystalline solids. Types of solid: ionic solid, covalent network solid, molecular solid, metallic solid. 1. Particles of unit cell. Ionic solid consists of cations and anions. In covalent network solids, atoms are covalently bonded with each other. In molecular solids, consists of either monoatomic or polyatomic molecules. In metallic solid, metallic ions of metal crystal is surrounded by sea of electrons. 2. Interparticle forces. Ionic solids, cations AD and anion are held together by electrostatic force of attraction. Covalent network solid, atoms are held together by covalent bonds.
Molecular solids are held together by either weak London dispersion force or dipole-dipole forces or by hydrogen bonds. In metallic solid, metallic bond is formed due to attraction between cations and mobile valence electrons. Hardness. Ionic solids are hard and brittle. Since covalent network solid is bonded by covalent bond, covalent solid is very hard. Molecular solid are soft due to weak London dispersion force. Metallic solid hardness varies from soft to very hard. Melting point. Melting point of ionic solid is high 600 degrees Celsius to 3000 degrees Celsius. Melting point of covalent network solid is high 1200 degrees Celsius to 4000 degrees Celsius. Melting point of molecular solid is low, minus 272 degrees Celsius to 400 degrees Celsius. Melting point of metallic solid is wide range, minus 39 degrees Celsius to 3400 degrees Celsius. 5. Thermal and electrical conductivity. Ionic solids are poor electrical conductors in solid state. Good conductors when melted, or good conductor when dissolved in water. Generally, covalent solid are poor conductors of heat and electricity. Exceptions: 1. Graphite, good conductor of electricity. 2. Diamond, good conductor of heat. Molecular solid are poor conductor of electricity and heat. Metallic solid are good conductor of electricity and heat. Example of ionic solid: sodium chloride NaCl, calcium fluoride CaF2, Example of covalent network solid. Graphite. Diamond. Silica. Example of molecular solid. Benzoic acid. Ice. Example of metallic solid. Sodium Na. Magnesium Mg. Copper Cu. Gold Au.